A beam of electrons, whose kinetic energy, K, emerges from a thin foil window. At the end of an accelerator tube, there is a metal plate, a distance d, from this window at a right angle. So what it's basically saying is we have an electron travels this distance. There's a window or a wall right here. Show that we can prevent the beam from hitting the plate by applying a magnetic field, B, such that B is greater than this. Okay, so the idea here is by applying a magnetic field, we're going to cause a force on the electron. Electron is a charge. A charge in a moving charge, an electric field, is going to experience a force. We want to create a force on it so that the particle does not reach the plate. And so the way we're going to do that is we're going to provide a magnetic field. I'm going to say C here. We want a force going down. And this really isn't going down. It's going to the center of a circle. So we're going to have circular motion with our electron. But at this top point, when it's approaching the plate perpendicular, as they said, it's going to be, the force is going to be down. So V cross B? No. V cross B. All right, so B is going to be into the page. And so the way I think about this, and it doesn't matter, we can do either up or down. Either way, it'll still miss the wall. But V cross B, so V cross B, first vector, then you bend your fingers in the direction of the second vector, which will be into the wall, cause a force going up. So in our picture, this is up. But since we have an electron, which is negatively charged, we're going to be a negative sign. The whole thing then becomes down. So, and we could flip the other direction, it wouldn't matter. Both of them would be correct. So that actually answers part B first. So now we want to find out how strong this has to be, but we want to do it in terms of K. So we're going to say that force equals QVB. V and B are perpendicular, so I'm going to drop the cross product. QVB, which equals mass times acceleration, put a little c there so that I know that it is centripetal, mv squared over r. R in this case is going to be the same as this distance d right here. But I'm just going to use r because I'm more familiar with it, feel more comfortable, doesn't matter. Not that my comfort doesn't matter, but I guess in the grand scheme of things, my comfort is irrelevant. Alright, so we're going to say that QVB equals mv squared over r. The v's cancel. What do we want? Oh, we want magnetic field. We're trying to find magnetic field. Yep. So we're going to try and find the minimum magnetic field needed just to get this to miss. So it'll be mv q, put the q there, over r. But we don't want things in terms of q. We want things in terms of the kinetic energy. Okay, let's go that. So I'm going to say that the kinetic energy can be represented at, and kinetic energy is due to motion, and I'm going to assume that can be represented as 1/2 mv squared. I'm going to assume it's not moving relativistically. We see that we have an mv here, so what I'm going to do is I'm going to multiply this by m over m. So rearranging this, we're going to have 2 energy kinetic. The 2 m's become m squared, v squared over m. Rearranging that one more time, at least one more time, 2 mass kinetic energy. Instead of k, I usually use e subscript k. It's the exact same though, it doesn't matter. mv squared, so that mv, just flip this around, it's going to be the square root of 2 mass kinetic energy. And from there, I'm going to plug this in. So I'm going to say the magnetic field, this is the minimum magnetic field, is going to be Q. Did I get that right? No, Q is supposed to be on the bottom. There we go. Good catch. All right. So this is going to be 2 mass square root of kinetic energy, square rooted, all over QR. I think this has square roots. Yep, it has the whole thing under square rooted. So what I'm going to do is I'm going to square the Q, I'm going to square the R, and to basically undo that, I square root it. And the idea is like 2 squared is 4, square root of 4 is 2, so you can kind of square and square root things. It's fine. You're going to have to trust me on this one. I'm going to take this. I think we're like 90% there. We're just going to make sure that everything matches up with the notation they want. They tell us it's an electron. So Q equals small e, and they give us distance d, so R is d. I'm going to say that energy kinetic is the same as K, and then I'm basically just going to copy everything that they have and say, therefore true. So 2 mass K over Q squared, no, E squared, D squared. Square rooted is magnetic field, and if B is greater than this, then it's just going to move in a tighter circle. So I'll do equal than, or less than, or equal to, with a little symbol like. So greater than or equal to. So that proves that B has to be greater than or equal to 2mk over E squared D. Yep. And then orientation is just perpendicular. It's either into the plane or out of the plane. It just has to do with it circles down or circles up. So, and that's how I approach this one. Hope that helped. Take care.